Hey everybody, welcome back. Today we're going to take a look at a couple different things. We're going to explore types of continuities, define continuity at a point, confirm continuity at an interval, and remove some discontinuities as well. So to start, here's a couple pictures of what, in real world, what it would mean to be not continuous. We can see a couple bridges here, a couple roads where pieces have been removed or just fallen. So these would be not continuous, okay? Continuity basically means that there's no interruptions, and you can see from these pictures there's major interruptions in each. So in a graph, there's three examples of discontinuities of a function or interval. Three different ways we can see where a function might be not continuous or discontinuous. Okay, in order for a function to be continuous, three things must be true. The first thing that must be true in order for a function f of x to be continuous at a point, x equals c, is that there must be a y value. So we say f of c is defined. So there has to be a y value at x equals c. Okay, and if it's not, we say this is called a removable discontinuity. You can see a picture here. At x equals c, there is no y value, so it's called removable. Why is it called removable? Because we can remove the discontinuity by simply filling in that circle there. Okay, but since there's a hole in the graph at c, we say that the function is not continuous at c. It's a removable discontinuity. The next thing that must be true for a function to be continuous is that the limit must exist. So the limit, as x approaches c, of f of x must exist. Okay, if that doesn't happen, you can see a couple pictures down here. The first one, at c, the limit does not exist because the left-hand limit and the right-hand limit are different. That is called a jump discontinuity. In the second graph, you can see that we're going to infinity or negative infinity, which means the limit does not exist. That is called an infinite discontinuity. And both of these discontinuities are actually called non-removable. Why? Because we can't just simply fill in a point to make the discontinuity go away. The third thing that must be true in order for a function to be continuous at a point is that the first two must be equal to each other. In other words, the y value must be the same as the limit. So here you can see this graph here. There's a y value at c. There's a limit at c, but they're not the same. Okay, this one is also called a removable discontinuity because, again, we could basically just take this point, move it up here, and remove the discontinuity. So discontinuities fall into two different categories, removable or non-removable. And if it's non-removable, we actually have two different words to describe that, a jump or an infinite discontinuity. Let's take a look at a couple problems here. Here's an old AP problem. Let f be a function defined by this piecewise function here. Show the function is continuous at x equals 0. All right, so the first thing that must be true is that there must be a y value there, right? So we look, where do we put 0 in? We put 0 into here. So f of 0 would be 1 minus 2 sine of 0, which is 1 minus 2 times 0, or 1 minus 0. So f of 0 must be 1. So the y value does exist. That's the first thing that must be true. The second thing that must be true is that the limits must exist at 0. So we want to check the left-hand limit as x approaches 0. And that would be by putting 0 into here, which we already saw is 1. And we want to check the right-hand limit by putting 0 into here. So it would be e to the 0 power, which is 1. So therefore, the limit as x approaches 0 exists, and it's 1. And the third thing that must be true is that f of 0 and the limit as x approaches 0 must be the same. And that is true because they're both equal to 1. So therefore, we could say f of x is continuous at x equals 1. All right, so we already talked about this before, but you recall from last year, even you might have learned this last year, that discontinuities have to be either removable or non-removable. All right, so what I'd like you to do here is maybe pause the video on your own, take a look at this word bank over here, and fill this in with some of the words that we've already learned today regarding discontinuities. All right, let's take a look at your answers. So discontinuities are either going to be removable or non-removable. All right, so we've used removable and non-removable here. And what would that look like in a graph? A removable would be a hole in the graph. And a non-removable would either be a jump or an asymptote, vertical asymptote to be exact. All right, example 1. All right, here we have example 1. It says the graph of f is above. Determine all the x values where the function is not continuous and classify each as removable or not removable. So first let's take a look at here, all the places where the function is not continuous. We see one here, one here, one here, and one here. So there's 4 discontinuities in this graph. There's 4 breaks in the graph. All right, now we've got to figure out which are continuous and which are not, which are removable and which are not. So the first one at -1, there's no way to just make 1 point change and remove this continuity. So this one would be non-removable. And at 1, since it's infinite, that would also be non-removable. And for number at x equals 3, if we just took this point and moved it up here, it would remove this discontinuity. So this one is removable. And at 5, if we filled in that point, that would remove the discontinuity. So that one is removable. So we have 2 non-removable and 2 removable. So let's start here by writing some sentences out. We can say f of x has removable discontinuities at x equals 3 and x equals 5. And also, it has non-removable discontinuities at x equals -1 and x equals +1. Everywhere else on that graph, the function is continuous. Number 2 is the same question, except now we don't have a graph, we have an actual function. So let's take a look at this function. And we need to see where there's breaks in the graph. There's holes, jumps, or asymptotes in the graph. So to do that, you're going to look at the denominator and see when that's going to be 0. So to do that, let's start by factoring everything. And we can see there's going to be 2 discontinuities in this graph. One at -2 and one at +5. So now we got to figure out which one is removable or which one is not removable, or if they're both the same. Well, let's think about what's happening on this graph at -2. At -2, if you put -2 into our equation, we're going to get some number in the numerator and we're going to get 0 in the denominator. So that means there's going to be an asymptote, a vertical asymptote, at -2. So what does that mean? That means that g of x has a non-removable discontinuity at x equals -2, because it's an infinite discontinuity. All right, the other discontinuity is at x equals 5. If you were to put 5 into your function, you're going to get 0 over 0. So what does that tell us? That tells us there is a hole in the graph. And whole, remember, is removable. So we can say g of x has a removable discontinuity at x equals 5. And then the second part of this question then says, write the intervals over which the function g of x is continuous. Well, the hard part of this problem is done. Once we know where it's not continuous, that means it's continuous everywhere else. So we know that g of x is continuous on all real numbers except -2 and +5. So we can say that is continuous on the following intervals: -2 to -infinity to -2, -2 to 5, and 5 to infinity. All right, example 3 of a piecewise function here, and we want to know where it is not continuous at, or discontinuous. So this is just a line. It'll be continuous everywhere in that interval. This is a parabola. That'll be continuous always. There's no holes or jumps in that parabola. This is a line, always continuous. This is a line, always continuous. So it's going to be continuous everywhere except maybe at these 3 numbers. So we have to check those 3 numbers and check and see if they fit the criteria for continuity. So let's start with -2. So let's start with x equals -2. All right. So does h of -2 exist? We put -2 into this one because that's where it says x is greater than or equal to -2. And we get 4 minus 9, which is -5. So the function does have a y value at -2. The first criteria is met. Second criteria is the left and right limits agree. So limit as x approaches -2 from the left of h of x. And for that, we're going to put -2 in here. And we get 2 times -2 minus 1, which is -5. And then also the limit as x approaches -2 from the right of h of x. And for that, we put -2 into here again, and we get -5. So the limit as x approaches -2 of h of x does exist, and it's -5. So last thing we have to check is, does the y value equal the limit? And it does. Therefore, the function is continuous at -2. Don't need to worry about -2 anymore. All right, now let's check 1. So x equals 1. If we put 1 into the equation, that would be into here, we would get 3 times 1 plus 2, which is 5. So h of 1 is 5. So the first criteria is met. There is a y value. Then we got to check our limit. So limit as x approaches 1 from the left of h of x, and limit as x approaches 1 from the right of h of x, and see if those are the same. So if we put 1 into here, we already said we would get, let's see, 1 squared minus 9, that would be -8. And if we put x into here, we would get 3 times 1 plus 2, which is 5. So left and right limits disagree. Therefore, the limit does not exist. Limit as x approaches 1 does not exist. Therefore, this function is not continuous at 1. What kind of discontinuity would happen here? It'd be a jump in the graph, which is not removable. We'll write that down later on here. Let's do our last check. We got to check one more point. That would be when x is 3. So first of all, does h of 3 exist? If you put 3 in, well, where would you put 3 in? There's nowhere to put 3 in. So h of 3 is not defined. And therefore, we already know it's not continuous at 3. But we do have to check the limits to see if this is a jump discontinuity or a removable discontinuity. So let's check our left-hand limit. And our right-hand limit. The left-hand limit would be 3 times 3 plus 2, which is 8. Sorry, that's 11. And the right-hand limit would be 4 times 3 minus 1, which is 11. So a limit does exist. So on the graph, what this is going to be a hole in the graph. Okay? So when we write our answers out here, we have a discontinuity at 1, which is a jump, and discontinuity at 3, which is a hole. So we could say h of x has a non-removable discontinuity at x equals 1. And then h of x has a removable discontinuity at x equals 3. And it would be continuous everywhere else. So negative infinity to 1, 1 to 3, and 3 to infinity. On our last one, example 4, again, it's asked to find two values, a and b, that make this piecewise function continuous. All right, so how do we do that? Well, we got to make sure that the y values would exist at 2 and 3, that the limits would exist at 2 and 3, and that those y values and those limits would be the same. So let's do 2 first. X equals 2. What would k of 2 be? Well, if you put 2 in, we would put it into here, and that would be 4a plus 2b plus 3. You're putting 2 in for all the x's there. Now the left-hand limit, as x approaches 2 from the left of k of x, we're going to put 2 into here. But we can't put 2 into here. So what we got to do is we've got to factor that. All right, that would be x plus 2, x minus 2 over x minus 2, which ends up being just x plus 2. So the left-hand limit would be the limit as x approaches 2 from the left of x plus 2, which is 4. And then the right-hand limit, we would put 2 into here, but we already did that. All right, and we got 4a plus 2b plus 3. So we know that an equation that must be true for this function to be continuous must be 4 equals 4a plus 2b plus 3. The left-hand limit at 2 must equal the right-hand limit at 2. Unfortunately, we cannot solve that equation for a and b. We have two variables. We only have one equation. So now we need another equation. We get the other equation from x equals 3. Same thing here. So first we would do k of 3. And k of 3 goes here. So that would be 6 minus a plus b. And then we do the left-hand limit as x approaches 3. And of course the right-hand limit as x approaches 3. So the left-hand limit, we put 3 into here, and we get 9a plus 3b plus 3. The right-hand limit, we put 3 into here, and we already got that, is 6 minus a plus b. So in order for the function to be continuous here, we need the left-hand limit to equal the right-hand limit. So now we have two equations, one here and one here, that both have two variables in it that we can solve this system of equations. All right, so the first thing I would do is simplify these two equations. So the first equation would be 1 equals 4a plus 2b. The second equation, if we do some rearranging here, if we added the a's on both sides, we get 10a. Subtract the b from both sides, we get 2b. Subtract the 3 from both sides, we get 3. So 3 equals 10a plus 2b. And now this is a nice, easy system of equations. We can multiply this by -1. When you add those together, you would get 2 equals 6a plus 0b. Divide by 6, we get 2/6, or 1/3 is equal to a. Put that 1/3 back into either equation. How about the top equation? We get 4 times 1/3 plus 2b. And just going through the solving steps for that. We get negative 1/6 equals b. So what does that mean? If we put 1/3 in for a and negative 1/6 in for b, this function would be continuous at all numbers. And that'll do it for our lesson on continuity. Once again, thanks for checking in, and we will see you next time.